Hello chemistry students, in this video I'm going to go through the presentation about predicting the products of reactions. Alright, so just a little review here. A chemical reaction is a process in which one substance changes into another substance. Okay, a couple of ways, actually 4 ways you can know that a chemical change has taken place. There will be a surprising color change, a change in heat content, such as heat or light are released, leading to warming, while some reactions, actually the mixture becomes cold, and that means they've absorbed energy from the environment. Gases can be produced. A lot of times you'll see bubbles from that, or a precipitate, a solid, might form out of a clear solution. Alright, so to review our synthesis reaction type. So the synthesis, two separate compounds or two separate substances will become one substance. And to get more specific, where we start predicting products, there are different types of syntheses, like where you have two elements and they combine to form a compound made from those elements, such as this one, H2 plus F2 makes HF. For this type, you would either use the draw the Lewis structures and figure out how many bonds would need to form to make to follow the octet rule to make the compound, or if it's a metal and a non-metal, such as here, you're going to make a binary ionic compound, and you will need to consider the charges. Like NaCl, it's not NaCl2 because sodium forms positive 1 ions and chloride forms negative 1 ions, so they go together in a 1-to-1 ratio. If this was magnesium chloride, it would be MgCl2 because magnesium has a +2 charge. Okay, when you have a metal oxide combined with water, the metal oxide is going to combine with the water in a way such that it makes a metal hydroxide. The 2 is here because calcium has a +2 charge and hydroxide has a -1 charge. So 2 hydroxides are necessary to make a neutral compound. By the way, you'd recognize the metal oxide because it is a metal bonded to oxygen, so that makes it a metal oxide. A non-metal oxide, like sulfur trioxide, well, sulfur is a non-metal, and it's bonded to oxygen, so that makes it a non-metal oxide plus water. That's going to make an oxyacid, or an acid with oxygen in its formula. This one is sulfuric acid. These are easy because you just take this and put it together. 3 oxygens plus 1 oxygen makes 4. There's the sulfur there and the 2 hydrogens, so there you go. Right, on your reference table, the different types of synthesis reactions are listed on page 6, and that's where the screenshot came from. So you can reference back to these. The binary compound is just 2 elements, A and B, combined to make a compound. The metal oxide and water, it says makes a base. Bases will have hydroxide in them. We haven't learned that yet, but I'm telling you now. So it'll be a metal hydroxide that you make there. Non-metal oxides and water, so that'll make an acid, and we have learned the acid so far. Decomposition reactions are going to have a compound break down into simpler substances. Right, and there's several different types of these, and you will need to be able to predict what will form from these different types. So binary compounds only have 2 elements. They'll break down into the elements that are from them. A metal carbonate will make a metal oxide and carbon dioxide. Metallic hydrogen carbonates, so see the hydrogen carbonate in that with the metal, they're going to make a metal oxide, water, and carbon dioxide. Metal hydroxides, so a metal with hydroxide, it's going to make a metal oxide and water. Metal chlorates will break down into a metal chloride and oxygen. Again, it's a metal chlorate because it has a metal bonded to the polyatomic ion chlorate. Oxyacids, so this is the reverse of the synthesis reaction, making the oxyacid, so it makes carbon. This one, it'll make water and whatever's left over from the oxyacid after you take the water out. And then hydrates will break down and release water and leave the ionic compound behind. In this case, it's copper sulfate. All right, so we'll use the reference tables to predict those, and here again are all those types listed out generally, and you have to be able to identify polyatomic ions like carbonate, hydrogen carbonate, hydroxide, chlorate, in order to be able to use these. Also, you'll have to know your acids to be able to do the acid decomposition. Single replacements, two ions switch places with each other. Actually, let me say that again. It's only one ion switches places with another ion. It can be a cation replacement or an anion replacement. Okay, and there's a few different ways that single replacements can happen, and what we're going to spend most of our time in this video talking about. Okay, here's what it looks like on the reference table on page 6. We're going to talk about how you can tell. Okay, I'm going to scoot ahead just a little bit and show you. On the reference table, this is what you'll be looking at on page 7, the activity series. So it tells you on this what the different elements listed here can do. So these elements down here, the coinage metals or the jewelry metals, silver, platinum, and gold, they're not very reactive, and that's good because you wouldn't want to wear them for jewelry if they were. Copper and these other metals here, they're about all they'll do is react with oxygen to form oxides. You might have noticed jewelry that contains copper in it, it'll turn green because copper oxide is a green color. Then once you get here, these metals will not only react with oxygen to form oxides, cobalt, nickel, tin, lead, but they'll also replace hydrogen from acids, so they're a little more reactive than the ones below them. And then these metals are even more reactive. They'll replace hydrogen from steam and replace hydrogen from acids and react with oxygen to form oxides. And then these are even more reactive, so they'll replace hydrogen from cold water. That means if you drop a chunk of sodium or barium or potassium or lithium into water, it will react with it and bubble as the hydrogen is released. I do the sodium water and potassium water reactions in class as a demonstration when we have class to show those reactions. Also, the activity series of halogens, fluorine is the most reactive halogen while iodine is the least reactive. That means fluorine can replace iodine, but iodine could not replace anything above it on the activity series. Okay, so we'll go back and look at a few examples of this. Alright, so metals can replace other metals if they are above the metal they're trying to replace. So lithium could replace magnesium out of a compound, but magnesium could not replace lithium. Okay, the metals above hydrogen can replace hydrogen and acids. We saw that on the reference table. And metals from sodium upward can replace hydrogen and water. We also saw that on the reference table. We talked about the halogens. Fluorine can replace iodine or bromine or chlorine, but they can't replace fluorine. Alright, so this one, what will form there? Well, the fluorine will replace the chlorine. It'll make sodium fluoride and chlorine gas. Alright, magnesium chloride plus bromine. Look, bromine is below chlorine, so bromine cannot replace chlorine, so there's going to be no reaction there. Alright, let's look at some metals. Alright, so in this reaction, iron would be replacing copper. And if we find so we're going to look at, okay, so can iron replace copper? Yes, because iron is above copper. So yes, that would form products. Nickel, can it replace sodium? No, because nickel is below sodium, so that's a no reaction. Alright, lithium replacing zinc. Yes, lithium is above zinc, so it can't replace it. So then you would make the products. Remember, these are ionic compounds. You do the charges, that's why it's Li2CO3. Alright, aluminum and copper, yes, because aluminum's above the copper and it would make products. Alright, let's look at some other ones. Okay, will magnesium react with water? Well, yeah, it will. Now, this says the water would have to be hot. Your reference table doesn't specify that, but you could still find the range. So there you go. Yes, if it's hot or if it's steam. Alright, so that would make products. Magnesium replaces the hydrogen, and it makes magnesium hydroxide. Alright, what about zinc and hydrochloric acid? Well, yeah, zinc is in the category with that can replace hydrogen from acids, so yes, it will replace the hydrogen. Alright, aluminum, yeah, it can replace water, the hydrogen in hot water, so yes. Copper and water, there's going to be no reaction because copper is outside of the range that will react with water. Calcium and sulfuric acid, yes, it's inside the range that will react with acids. And sodium with water, yes, because it's in the range that will react with water. Okay, with double replacement reactions, you got to form some kind of product that is no longer soluble in the solution or no longer forms ions in the solution. Either precipitate, insoluble gas, or molecular compound. Usually that molecular compound will be water. Okay, so let's look at some examples here. This one forms the precipitate lead iodide. This next one is an acid-base neutralization. It forms water, which is a molecular compound. Notice that the S here says that this is no longer dissolved in the solution. That's because it's insoluble. The L here is saying this water is newly formed as a result of these things, and it would just go and mix in with the rest of the water in the solution. So we have formed something new here. This is neither acidic nor basic like the reactants were. Now, in order for a precipitate to form, you have to have something form that is insoluble. So to do that, you'll consult the solubility rules on page 6 of your reference table. Notice that lead iodide that we looked at on the previous slide. Okay, if you look at the solubility rules here, it says that soluble compounds include all chlorides, bromides, and iodides except silver, lead, and mercury 1. Well, what that means is that lead iodide is not, see it's an exception, is not soluble, so that's why this would be the precipitate. Potassium nitrate is soluble. See, all nitrates are soluble, so potassium nitrate, and it's also group 1 salt. So potassium is a group 1 metal, so that makes potassium nitrate a group 1 salt. So it's soluble. There's no, it doesn't form a precipitate. So you have to form a precipitate in order for a double replacement reaction to go forward, or form water, a solid precipitate or water. Yeah. Okay. Now, combustion reactions, the products are always going to be carbon dioxide and water. You have to be able to recognize, hey, there's a hydrocarbon, it has carbon and hydrogen, and occasionally oxygen in this compound, and it'll react with water. All right, in net ionic equations, we're going to represent only the ions that are actually involved in the reaction. All right, so in this particular reaction, the sodium hydroxide and the hydrochloric acid, the ions that form in the solution from that, there's hydroxide ions and sodium ions and hydrogen ions and chloride ions. The ones that react to form the new product are the hydroxide and the hydrogen ions. So that's why we show the hydroxide and the hydrogen ion, and it makes water as a product. The sodium chloride, the sodium ions were in the solution before the reaction and after the reaction. Same thing for the chloride ions. So nothing has changed for that. So that's why we don't include it in the net ionic equation. Now, the other one here, when you form a precipitate, you show the ions that form the precipitate. Again, the sodium and the nitrate ions were in the solution before the reaction and after the reaction, so nothing changed with them. The only thing that changed was the silver chloride precipitated out. It started out as ions. Now it's a solid, no ions. Thanks for watching.